Welcome to this session, Diagnosing Your Application on the JVM. My name is Staffan Larsson. I'm the Serviceability Architect at Oracle for Java SE. I'm going to talk today about some of the tools that are available in the JDK that you can use for diagnosing, well, both the JDK itself, but most importantly, your own applications. I'm sorry for these very small screens. I'm going to show you some demo code, some command line code, and I hope you can see it. If you can't, then move closer. So we've all been there, right? Your application is up and running, there are no problems, everything is fine, but then suddenly a customer calls you or tweets or something about some problem. Hopefully you have everything set up, you have all the tooling in place to go looking for the problem. This session we're going to look at the tools that are available in the JDK, which means that they will always be installed, always ready to be used, if you know how to use them. I'm going to talk about the tools. I'm going to give you demos of how to use these tools. However, there are quite a few tools, and I won't have time to show you all of them in detail. The goal here is to help you get an introduction to the tools, and then you can go and explore more by yourselves. Most of the time I'm going to spend on command line tools. There are some visual tools which can be more powerful, but they're also easier to find out by yourself by clicking around in them. And sometimes the only thing that really matters is a command line. That's all you have available to you. Apart from showing the tools in action, I'm also going to talk a little bit about the internals of the tools, how they interact with the JVM, how they get information out of the JVM. And then at the end, I'm also going to talk a little bit about the future, what's things that we are working on right now. So I'm going to start with demos. And I hope you can read this. Is it big enough? Yes. Okay, good. So the first thing we're going to look at is how to discover what JVMs are running on your system. You may already have run JPS, which is the simplest command for finding out programs that are running. It lists the Java programs and the process identifier of the program. You can add some more options to it to show the arguments to the programs, and you can also see the arguments to the virtual machine. JPS has been around for quite some time, so you may have seen it before. Something that we've added in now in JDK 7 is a command called jcommand. At its simplest, it's just like JPS. It will list the processes that are running. It will include, by default, the arguments to it. But jcommand is much more powerful than this. It can actually send commands to the JVM for processing in the JVM, and it will get text output back from the JVM after running these commands. So it's typically used for diagnosing the JVM and the application. I will talk a little bit more about the implementation of this later, but right now we'll just look at how to use it. So you say jcommand, you say the process identifier, in this case the sleeper process, which is a dummy program that doesn't do anything, and a command, so vm.version. And we get back the version of the VM and the JDK actually. We can also see another command line. So we get to see the command line that was used to start this program. Personally, I find it quite tedious to always type in the process identifier here. So there's a shortcut in JCommand for just saying the name of the program instead. Will give you the same output. And actually this is a substring match, so I can type something smaller and I will get the same output. If you want to send the command to all the processes at the same time, you can do that by saying 0 and VM uptime for, VM uptime. We get the uptime for all the processes that are running. They were started at the same time, so they have the same uptime. So that's all good. But what other commands are there available in JCommand? Well, there's going to be a different set of commands available for each different version of the JVM, since we're going to add more and more commands. But JCommand has its own help system, and it can actually query the JVM for which commands are available. So if we, if we ask the sleeper process for help, it will list the commands that are available. Help. Yep. There are not that many commands right now, as you can see, but we're working on adding more and more. And if you want to know what they do, here's just a list of names. You can still use the helps command, so we can ask the vm.flags, for example. Oh, sorry, the other way around. We can ask the sleeper for help on VM flags. We get a little output here that says that it prints the VM flags and their current values. This is nicely syntaxed if you have a wider screen, or nicely formatted if you have a wider screen. It also says the options, so there's a -all option here, for example, for showing you all of the flags. So let's see what it looks like. Oops. Those were the flags that were set when we started the program. We can also do all, and we get a whole list of all the possible VM parameters that you could have used. Over 700 actually. Not sure what all of them do. Could be useful sometime, I don't know. So there's one additional feature that is very useful in JCommand, which is especially useful if you want to script the running of JCommand for continuously monitoring, for example, or something like that. You can specify a file with the commands in. So if you have a file like this, for example, just lists a number of commands you want to send, you can go command sleeper -f and the file, and it will execute them one at a time. So first uptime, then the version, and then arguments down here. This could be formatted better, I think. We'll work on that. So what else? We can do JCommand VM system properties for listing all of the system properties that are available. Can be very useful sometimes for digging into problems. Typically, looking at the class path can be interesting. If you have lots of scripts starting up, you're not really sure what ended up on this class path. In this case, it was simple. So those were some simple things you can do with JCommand and some of the other tools. Now I'm going to look a little bit more at output from these commands. So you have probably used JStack for getting a stack trace. So this requires a process identifier. There we go. We get complete thread dump from the JVM. You can do the same thing with JCommand. It's called thread print. Get the same output. It's just different ways of executing the same thing. So if you look at this output, you typically you get the stack traces for each of the threads. So in this example here, we have a main thread. It has the Java priority of 10. This is an internal identifier of the thread. This is actually the operating system's thread identifier. We get to see that it's currently sleeping in thread sleep. That's what the sleeper does. It sleeps. Not very interesting. What may not be as well known is that the stack traces also include a deadlock detection feature if you have a deadlock. I have a program which has a deadlock, incidentally. So, I can't spell, sorry. Thread print. There you go. So at the end of this long printing of threads, we see that the JVM found one Java level deadlock. In this case, thread 1 is waiting to lock a monitor, a Java lang object, which is held by thread 0. Thread 0 is waiting to lock another monitor held by thread 1. It's a classic deadlock. A deadlock may involve more than 2 threads, so it may be a lot more complicated than this simple example. You also get a list of the stack traces for the threads involved in the deadlock below here. And deadlock detection actually works if you're using Java util concurrent locks as well. The previous example was just normal synchronized statements in Java. Same thing with a process that has that uses Java util concurrent locks reentrant lock to cause a deadlock. You see the same thing. Thread 1 is holding on to a lock that thread 1 wants a lock that thread 0 is holding on to, and thread 0 is holding on to a lock that thread 1. Same thing. You also get the stack trace in this case, but it's a lot more stuff in there.
You mentioned that this is available in JDK 7, right?
J command is new in JDK 7, maybe 7U4, I think, maybe. Is that true? Okay, 7U4. Although, yeah, I'm running a pre-build of 7U10, whatever. Another thing that you can find out from these stack traces is you can use it to determine the CPU usage in terms of threads. Normally, you have a process that is using a lot of CPU. You only see from the operating system that, well, there's a process using lots of CPU, but you can't really figure out which thread inside of the Java program is using that CPU. So to show you that, we'll start a little program that uses up my CPU. I don't know if you can see the little monitor up here, but it turned blue, meaning that someone's using CPU resources. We can use PS with some options, and we will filter out only, this is almost unreadable. Anyway, there is one thread, so this lists all the threads running inside the Java process, and it lists the CPU usage per thread. So there's one thread here using 98% of the CPU. This is the thread ID of that thread. Can you remember the number for me? We will then go look for that thread in the output, and we quickly discover that these are hexadecimal numbers, and the thing we were looking for was not, it was a decimal number, and I can't remember what the number was. 7220? Okay. Good, good, you're awake. 7220. So 1C34. And here's the thread inside the program. It's the main thread in this case. You could have guessed that by looking at the stack trace. But anyway, sometimes it may be useful. Let me kill that process so I don't keep burning CPU. So the JVM also publishes a ton of quite detailed performance data from inside of the JVM. This is garbage collections, what code is jitted, and a lot more information. And you can actually get at this information as well with a tool called JStat. I'm going to take a look at young space collections with the help of JStat. So if we take a look at what processes are running, we ask for GC new data from 6774, which is a GC process, and we want it every 1 second. So we get some data, which is almost unreadable again because of the. But anyway, every second this will sample performance counters from inside of the JVM, and we can see this column here called EC is the current capacity of Eden. It's always the same in this case. The EU is the usage, Eden usage. You can see it fluctuate over time, and now you can't see it, but over here and this column here is the sequence number for the garbage collection, or the young space garbage collection, and in this column here is the time. So it took 0.7 seconds to do this garbage collection in this example.
In the previous example, you said that with random you can find out which thread was using the maximum CPU.
Yeah.
But I couldn't find any information that showed that that was using 19% of the CPU.
So we correlate. So the question is, in the previous example, I showed how you could find a thread used a lot of CPU. And what I did was correlate information from PS, which showed the CPU usage per thread, and then information from the stack trace showing you which thread that was in terms of Java thread. So the JVM itself doesn't provide that information, but using the operating system and the JVM commands together, you can find out. So another example of information from JStat. We start a little program that does something, and we can say print compilation for 7304 every 1 second. We see the JIT compiler doing its work, compiling a number of methods in this example. I don't know if that's useful, but you can also list, so there's a whole set of options. JStat-options will tell you the available options. So you can see class loading, for example, when it happens, and a lot of other information from the garbage collector that I didn't show. You can also take a peek at the raw data that this is using by using the J command perf counter print. We get to see all of these counters, so they're typically some name of a counter and some value. And there's 200 of these, I think, something. So now that we're talking garbage collection, I'm going to look at some other commands that are useful for looking at the heap. The first is a class histogram. This will show you what the number of instances for each class that are currently loaded on the heap. It will also show you the total size for each instance type. This can be useful as an initial way of finding memory leaks. Typically if you see one class growing over time, that's an indication of a memory leak for that type. And I have a little program here that leaks memory. Let's start it in the background. Then let's look at a class histogram for that. So in this example, we see that we have 92,000 instances of hash map entries and almost the same amount of instances of a class called key. And the hash map entries are taking up 2.9 megabytes of space. If we do this again, same command, we see that now we've grown to 300,000 instances. And if I keep doing this, you'll see the number go up. It's a typical case of a memory leak. You can get the same output. I showed the J command. You can get the same output with jmap-histo, I think. But then you need to specify the process identifier. I didn't have that. But it's another way of getting to the same information.
But this blocks the application thread.
While taking this snapshot, yes, it's like a garbage collection. Sorry, the question was, this blocks the application threads while you do this. Yes. It's like doing a garbage collection, going through the whole heap, counting all the instances. So if you figure out that maybe I have a memory leak, you probably want to create a heap dump that you want to analyze later in more detail. You can also do that with J command. So let's do that for the sleeper process in this case. gc.heapdump, and we also have to give the name of the file we want to save it in. And this, as you can see, this does a full garbage collection, and it creates a heap dump. It's there, 1.1 megabyte, not that big, very small heap in this stupid example. Typically, to look at that heap, you want to use a visual tool, such as Visual VM, for example, or there's an Eclipse project called Memory Analyzer Tool, I think, MAT, which is also very useful for looking at these kinds of heap dumps. Which brings us to Visual VM, which I will demo a little bit. So Visual VM is also a tool included in the JDK. A graphical tool in this case. Here you get a list of all the processes running on the system. You can click on one to show you more information about it. You get to see the system properties down here, for example. You can get a live monitor. I hope you can see the tiny graphs. We see the heap usage here, for example. You see each garbage collection as it happens, and the heap usage goes down. So let's take a look at how we could use what Visual VM would look like if we look at a memory leak. So I will start the leaking program again here in the background. It showed up here instantly. We'll go. Sorry?
The old one. That's the one that's been running.
Ah, I have two.
Yeah.
That's unfortunate. No, I don't want to kill that one. What do we have?
What?
Dead. I think. Yeah. So let's start it again. Fresh. A fresh leak. Close that one. Thanks.
Was the kill Java something you have?
Yeah, it just uses a J command to list the process identifier, finds out that, and does kill -9 on it. So we can look at the monitor for this, and we see the heap here growing over time, and growing and growing and growing. It never shrinks. The blue line is the used heap. We can then do a heap dump. Looking here. Get a heap dump. You can see, you can't see. Sorry. There you can see. The instances on the heap in this. It's the same histogram that we looked at earlier. And if we take another dump, we can compare this with the previous dump in a little while. We see that between these two dumps, we increased the number of instances for these two classes by almost 200,000. You can then use this to drill down into the instances. Or we can click on something here that's leaking. You can hardly see this, can you? I'm sorry about that. Not much I can do about it either. You can go try this at home. So anyway, with this view, you can look backwards from one instance. You can look backwards to who is referencing it. In this case, we have something called key, which is referenced from a hash map entry, which is referenced from a hash map entry array, which is referenced from the field table in a hash map, and we get all the way down to my little program called leak, which has a hash map that's apparently leaking memory. I'm going to kill that so we don't have that running anymore. Another useful feature in Visual VM is a profiler. Let's take a quick look at that. Sampler profiler, we can profile either memory or CPU. In this case, we see, well, I don't know what these, the little program I'm looking at is doing XSLT transformations, so maybe these names are a little bit weird because they're generated. But you get a call graph here of who is calling who and where time is spent. I'm not going to dig into details of exactly what this means. You can figure it out by playing with the tools and reading the manual by yourself. Sorry. Okay. Yes, JConsole is another graphical tool that's available in the JDK that does similar things. It's a little bit less advanced, but it does show you the same kind of graphs. So, so far, we've only looked at live JVMs that are currently running, but the JDK also has some tools that can look at core files. If you happen to have a core file of a crashed JVM around, that shouldn't happen, but it might. You can, if you don't have a core file, you can still use these tools with a Gcore utility in Linux, for example, to create the core file, to create a snapshot of your process, and then maybe later analyze it. There might be use cases for that. I have a core file, 13 gigabytes, something. No, megabyte, whatever. We can run JStack on this, for example. And to do that, you need to specify the executable that you use to start. In this case, my Java is here. And you specify the core file. And here's a thread dump for that core file. It looks like someone was playing Sudoku. I wonder who could have done that. JStack can also show you the native frames, so you see the JVM in action or a JNI library if that's what you're doing. You add -m and you get some output that's a little bit harder to interpret, but typically you see some native frames on the stack here. And you also see some names that are very hard to read because they're mangled, unfortunately. That should be fixed. Okay, so that was the end of the demos. I'm going to switch back to my presentation, and I'm going to talk a little bit more about internals, how this all works behind the scenes. But before I do that, I wanted to mention remote access to the JVM. I've only showed you local access now because it didn't make sense to do anything else on just one laptop. There are two ways you can access JVM remotely. The first one is JMX. This is what Visual VM and JConsole uses. Through JMX, you have access to all the information from the Java Lang management mbeans, which is garbage collection information, threading, operating system. There's a lot of stuff in there. JMX uses both SSL and authentication to make sure that it's secure. You can either enable JMX at startup, with some parameters, or this is new, you can start it by a J command. So J command management server.start, and you need to specify a lot of parameters to get it started. Very useful if you forgot to do that before. We are also adding support to the JMX access here for running diagnostic commands, or the J commands. All of those commands are also going to be accessible over JMX. The other way to access the JVM is to use JStatD. This is a daemon for JStat, so you run JStatD on your server typically, and you can connect to that with a normal JStat application. So you connect to the server to the JStatD, which will talk locally to the JVM and send back the information. JStatD has no encryption or authentication, so be a little bit careful there. So let's look at the internals. How does JPS and JCommand find the JVMs that are running on the system? Well, each JVM that starts will create a file in a well-known location in /temp hsperfdata, your username. You may have seen these files lying around wondering what they were. And so JPS and JCommand, typically all they do is list the files in this directory. And that's how they know they're running JVMs. So each JVM that starts will create a file with the name of its process identifier in that directory, and it will delete it when the JVM stops running. Unfortunately, JVMs can crash or be killed, so if there are any dangling files in there, they will be garbage collected when a JVM starts. So a JVM that starts will create its own file there. It will also look through all the other files to make sure that those processes are still running. And because both JCommand and JPS are Java programs, the JVM they run inside will clean this up before they actually look at this directory. So that's how they find the JVM, but how do they actually communicate with the JVM? In most cases, the answer to this is attach, the attach framework. This allows for sending commands, let's call them that, to the JVM. The JVM will process these commands internally and send back some text output to the tool. Attach only works for locally on the same machine, and only works for the same user as running the JVM. So that's how it is secure. This is what JCommand, JStack, and JMap uses. The mechanics for doing this is different on different platforms. On the Unixes, let's take JCommand as an example. JCommand then will create a file in /temp called .attach PID, and the PID of the JVM it wants to attach to. It will then send the SIGQUIT signal to the JVM. Usually when a JVM receives SIGQUIT, it will do a thread dump. But if it finds this special file, it won't do a thread dump. Instead, it will create a socket in /temp.javapid. And this socket is then used for communicating between JCommand and the JVM. So sending the command over that socket and getting the result back. Solaris does the same thing, except it uses the door API on Solaris instead of a socket. On Windows, it's a little bit different. Here, the remote process will actually inject some code into the JVM, into the process space of the JVM, through some operating system calls. It will then create a thread inside the JVM. This thread will call the injected code. The injected code would look up a JVM function called JVM enqueue operation, and that's how it will send the command to the JVM. The result will then be read back from a pipe. So these diagnostic commands that you can execute over or via attach, this is what attach will execute in the end. These are helper routines created inside of the JVM. They can do almost anything that's possible to do within a JVM, but typically they're for diagnosing, so they do gather some information and print it back. As I said, these can be executed with JCommand or soon with JMX. They have a self-describing help facility, so every time one of these diagnostic commands is created in the JVM, you have to specify all the parameters and some little help text for them. And as I said, there's different commands for each platform or for each version of the JVM, so it's very useful that there's a little help command so you know what's available. Now let's look at what JSTAT uses to find its information. That discovery file I talked about, it's not an empty file. It's actually a memory mapped file that has all the runtime information that we looked at with JSTAT. So the JVM creates this file, it maps it into its memory, it will continuously update these counters in memory, and JSTAT will just read it from this file. So here's a little diagram showing you all the access paths to the JVM. You can see that there's JMX, there's attach, and there's JVM stat, which are the different paths into the JVM. On the left, there's a J command, for example, using attach to connect to the JVM. In the middle here, we have JSTAT D, also talking to the JVM. And on the right side, we have another machine where JSTAT, for example, is used to talk over RMI to JSTAT D, which then talks to the JVM. There's also a JMX client like Visual VM or JConsole or Mission Control. So a little recap of the different ways to talk to the JVM. There's attach and JVM stat for local access. Of these, only attach is a two-way protocol. JVM stat can only read information. For remote access, you have JMX and JSTAT D. Only JMX in this case is a two-way protocol. You also have the Serviceability Agent, which is what's used to talk to core files or read core files that I showed you earlier. It can also actually talk to a running JVM if it wants to. It uses a debugger to talk to the core file or the process. So this should be used as a last resort if you actually have to. Typically, a JVM that's hung, you can't attach to it because that requires the JVM to actually be running. But using a debugger, you can attach to it, you can get information out of it. And that's what the Serviceability Agent is. You use it with JStack by saying the executable on the core file or -F for force and the process identifier. And a little diagram showing you how a JStack, for example, in this case, is built on top of Serviceability Agent, which uses a debugger to attach to the JVM. So a little look at what's coming in the future. The first thing I want to talk about is the Java Flight Recorder. There was a session earlier today about the Flight Recorder you may have listened to. If you have used JRocket, you may recognize this as the JRocket Flight Recorder. Flight Recorder, anyway, is a JVM built-in profiler and tracer. It's built to have very low overhead so that it can be always turned on. It uses circular buffers in memory to capture information about the JVM and the application that's running on top of the JVM. The typical use case for this is you discover something is wrong in your application. You can then dump the information from these buffers, and then you will have the information leading up to what went wrong. So you have some information, you can see what happened before it went wrong. It can be very useful. And that's what the name comes from, apparently. So it will capture both information from the JVM and the application, so garbage collections, locks, compiler events, exceptions, CPU usage, I/O information. Also something that's going to be added to over time. Another list of things that's coming, Java Mission Control. Again, if you use JRocket, you may recognize this as the JRocket Mission Control. This is a graphical tool that provides very detailed runtime monitoring information from the JVM. You can think of it as JConsole, but on steroids. It's also the graphical front end for JFR, or for Flight Recorder, which you can use to visualize, you can query information, you can sort things back and forth, you can create graphs of the information that you've gathered. As I said, we're also adding more diagnostic commands to JCommand. The goal is to make this a very powerful tool. Eventually, we're planning on replacing JStack, JMap, JInfo, all the other tools with just one front end. But it has to be at least as good as the other tools before we can do that. JMX 2.0, something we're picking up again. It was started a very long time ago. We're trying to revive that project now. So if you have any thoughts about what should be in JMX 2.0, let us know. It's very interesting. We're also working on improving the logging inside of the JVM. So the current state of logging in the JVM is a little bit sad. There's one subsystem for logging for each subsystem in the JVM. So everyone has written their own little logging features. There's a proliferation of different flags. Not all features are available to all subsystems. So, for example, only the garbage collection logs have rotation. None of the other logs have that. So we're trying to unify this to make it easier to use it and also for us easier to maintain the code. There's a Java enhancement proposal, I think JEP is short for, called 158, which you can go look at if you want to have more information about this. The last thing I wanted to mention is the Java Discovery Protocol that we're working on, which is a little way for a JVM to broadcast information on the local area network about here I am, so that graphical tools such as JConsole or Mission Control can find it and connect to it easily. We're going to publish a JEP for that within a few weeks, I think. We're working on it right now. Right, so I think that was the end of this. I hope that you have learned something new and hopefully something useful. If you haven't learned something new, then that's good. You know everything. And by the way, we are hiring. I also hope you learned something useful, and if you didn't, I would like to know what would be useful for you. So please let us know and go and experiment with the tools. And questions? Yes?
Our earlier production environment does have only JRE, and so I don't have any of these tools handy. Do you think we have any plan to put those tools on the JRE as well?
Okay, so the question is, I run only with the JRE in production and I don't have access to the tools?
Yeah.
You can just copy them over. Yeah. That, and you need the tools.jar file. Should work. Any other questions?
A lot of time it fails to detect the process, the JVisual VM.
Sorry?
JVisual VM is failed to detect the process that's running. It says that the username has a capital or something. So when you run JVisual VM, it comes with a list of processes.
Yeah, listed processes, yes.
But sometimes all JVMs don't appear over there.
Sometimes you don't see all the JVMs in Visual VM.
And I get an error saying that from the username, the temporary directory has a capital.
Okay, so that sounds like a bug. Send me an email and describe it. We can file a bug for it.
There is some guidance on it already.
Okay.
in JDK 1.7, doesn't Visual VM is not able to recognize anything. So
In JDK 7, Visual VM doesn't find any processes. Okay. Apparently, it did for me with in 7 update 10, so it may be fixed.
It works in your case?
Yeah, did you see?
But it runs on Ubuntu, right?
Oh yeah,
On Mac.
on Mac. Yeah, I did show the demo on Linux for a reason.
Okay.
That may have been part of the reason, yeah. The Mac support is a bit behind, unfortunately. We're working on it.
Is there a way to show slow methods?
To show slow methods. So in Visual VM, you can do a profile, which will show you where time is spent, CPU time is spent, and that is an indication of a slow method, or at least a method where you're spending a lot of time. It may not be slow, it just does a lot of work, but. Okay. Yeah.
You said that the JVM uses JMX for remote access. How does the JVM get started? Does it start by default, or does it start by setting up JVM?
So I think Visual VM starts, the question was how I said Visual VM uses JMX. How does it actually start JMX? And I think it does it it uses the attach framework, I think, to load using the Java Lang instrument API. You can load a jar file which hooks into the JVM, and then that jar file can start the JMX process. It's a bit convoluted. If they would redo it now with the support we added for management server.start, I think that's the way to use it.
It should start it up automatically for the process.
It can start it for local processes, but it can't start it for remote process, yes. You had a question? Yeah?
Do you have timelines for the flight recorder?
I can't provide timelines, sorry. That's what the big legal thing said in the beginning. Yeah?
What are the caveats for running this against like production servers? You mentioned that, for instance, like the heap comes out in full GC and so.
Yeah, so what's the problem, or what's the limits of running this in production? So yes, some of the tools does a full garbage collection, like dumping the heap, doing a class histogram. If that's a problem, then yeah, that's a problem. Using JMX to monitor should have very little overhead. It's going to create a couple of threads in your process, but other than that, I think the overhead is very small. Flight recorder, of course, is built to be very low overhead, so and designed to be used in production, so that should be fine. I wouldn't use the Serviceability Agent in production if I absolutely don't have to. Okay? There.
In JConsole, there was an option to access directly the JMX, the beans exposed via JMX, and I could not find that in the Visual VM. Is it just me that I couldn't find them, or they have to?
So in JConsole, you can access the mbeans directly, but you couldn't find that in Visual VM.
Yeah.
And I actually don't know if that's available or not. There's a ton of different plugins for Visual VM, so perhaps one of those solves it. I don't know. There is a plugin that shows you the mbean. Okay. Yeah.
This is more of a JMX question. Every time when I try to enable JMX, it has 2 parameters, JMX host and JMX port.
Yeah.
It takes the JMX port into account, but JMX host, it always takes local host. It ignores that parameter no matter what IP I get.
Okay. I don't know. Sorry. I wasn't aware of that parameter. There are way too many parameters to starting JMX, I think. Yeah?
You showed us the histogram over what objects, filling up the heap. Is there any way to determine
No, that's
For example, if you're interested in knowing what's filling up on a
so the question was, in the heap histogram, can you see what generation, garbage collection generation these things are in? And no, there is no way, but I totally understand your use case. That would be an interesting addition to have, yes. Yeah?
Will flight recorder be available for free?
No. I think the model is free for development, but charged for in production. I believe that's the... Okay. Thank you very much.